Right. So, last time I gave you an example of how if you wanted to make a permanent field calculation, how to take a freely available data set, export it, bring it into your online organization and run a field calculator tool to create that new column, right? And so I'm just going to add that data we worked with. And so that involved quite a few steps, right? And we made permanent changes to the data. One of the things you might run into, however, is that some data sets don't allow you to download copies, right? They will share it so you can view it and work with the data, but you can't make permanent changes. You can't download it and bring it into your organization. So there's another technique you can use if that is the case to calculate these derived indices to really customize the data fields for whatever mapping approach you are taking. So I wanted to show you that briefly before I get into the PowerPoint slides for today. And let's just pretend that like this layer here is hosted on an Esri server and that doesn't allow you to download and manipulate the data. What you can do instead, all right, here's our fields list. And we actually calculated population density last time. What you can do instead to kind of create a temporary calculation that isn't actually stored in the layer. This is really useful for if you don't have editing privileges for the layer you're working with, is under the pop-ups tab over here on the right side. And you can also do this in desktop. It's just in a little bit different place. There's this thing called attribute expressions. And so the difference here is that, instead of actually manipulating the underlying data table, writing new information to a new column in the data table, this is kind of a temporary definition of a mathematical operation that can be stored in the map document itself. So again, useful for when you're working with data that cannot be edited. Sometimes it's just a little bit more streamlined to do this. So in this expression builder, which looks a little bit intimidating, right? You can actually do these simple mathematical calculations. So if you're following along, you're right, if you pulled up that same layer we were working with last time, what you would need to know is the actual field names. And so you've got a few templates on the right side over here that help you with this. But if we go into the feature, it'll tell us a list of our field names. So we can scroll down and find that top 00 whatever, 001, 0001, and click on that template here in the profile variables. We can find our area as well. The one we calculated last time to convert to square miles was the area 2. So I'm just adding those. The syntax is just a $sign to indicate you're working with a feature layer. So $sign feature, period, and then the field name for each one. And then just that / to divide these by each other. And there should be a way to verify this somewhere. You just hit that run button. And it'll give you a preview for the first line of your data, what the result is. So the fact that this actually spit out a result tells me that my syntax is correct. It's going to divide the population field by the area. We can give this a name, right? Population density. And we can hit done. And now what you can do is you can use that in your pop-ups. You can also use it in your styles. So see, we have the choice here of an attribute field or an expression. So attribute field, again, is that permanent storage of a calculation. The expression option to the right is useful for when you can't manipulate the data or if your data is constantly changing, right? As soon as I actually calculate a new field and write those field values to a column, they're kind of locked in. They're not dynamic. The advantage of an expression is that if that layer has updates to the population field or the area field, the expression will automatically update as well. It's kind of just instructions for the software, like, hey, divide these two columns together. So we can choose that expression. Actually, once you define the expression, it's going to show up in your list of fields. So that expression we just defined, I'd named population density. You can add that, and then we can use this to actually symbolize. So what we're talking about today is how we break up these classes, right? The default that you can see on the screen right now is just taking a color ramp and stretching it between the smallest value, which is 2 people per square mile, and the largest value, which is about 2,000 people per square mile. So based on the distribution of your data, it's going to be advantageous to either use one of these color bars or to try to break up your data into bins to apply different colors to them to highlight different trends in the data. And depending on the purpose of your mapping approach, you know, your choice of classification or how you actually symbolize these data might change. Make sense? Right, so expressions and field calculations, you know, this is the stuff that you don't really get in the textbook that I like to highlight in class because it's kind of like the how do you actually do stuff in GIS portion of the class. That's why I'm focusing on it. You know, when I'm making maps, I do this stuff almost every single time, and it's hard to find a textbook that'll actually walk you through it. So we left off without actually looking at the distribution of data in our descriptive statistics section. So when we're doing descriptive statistics, right, we went through, oh, actually, I got to show you one thing I was looking at this morning. Hold on a sec. So my dog got me up super early this morning at like 5:30, and I was just scrolling on my phone, and I came across this. I was like, look at this. The first choropleth map I've ever seen where Montana is basically the only state that is highlighted by one class. And that's because actually right now we have a pretty bad COVID outbreak going on. Notice that this map is showing reported COVID-19 new hospital admissions rates per 100,000 population. So how would you calculate this, right? You take the number of new hospital admissions within a certain time period, divide that by the total population, multiply it by 100,000, it would give you that rate, just like we talked about in last lecture. And unfortunately, Montana is the only state right now, except for, I think that's Washington, D.C. blown up on the right side there, because it's so small. Could be wrong. But yeah, we fall into this medium class here. Design note, really hard to read this, right? Especially hard on a cell phone screen. This text is super small. Why is there so much space here? I would have made a much larger legend for this map, so it's a little bit easier to use. But yeah, if you're feeling, stay safe out there, wash your hands. If you're feeling sick, let me know. You don't have to always go to lab, etc. Okay. So things that can tell us about the shape of our data set. This is really going to control how we symbolize our data. So for basic descriptive stats, what we want to do is describe the central tendency, dispersion, and the shape of the data set. So where is most of the data, right? That's the central tendency. How spread out are the values? Are they really clustered close to that central value? Or is it a really spread out data set? Is there a large range of values? And what is the shape, right? Is it a nice bell curve shape? Is it a rectangular shape on a frequency diagram like this? That's going to all impact how we choose to symbolize our data. What we're showing here is just a histogram of exam scores. And classification with maps is the same thing as defining bins for a histogram. right? We might say that we want to represent all values between 0 and 59 with one color, all values between 70 and 79 with another color. This was a pretty challenging exam, right? The majority of students got a C. So how do we describe central tendency? We do this using the mean, median, and mode. So mode is just the most common observation in a data set. If you were looking at a frequency plot, that would be the peak of your frequency plot. And I really want to emphasize normal distributions of data. For most natural phenomena, they will define a normal distribution, right? Where we have sort of an average value, and we have less and less observations that fall into values that are far from that mean. Some other data sets might be different, right? But for most natural phenomena, including population characteristics, things of that nature, we typically do see these normal or sort of close to normal distributions of the data. A perfect normal distribution has the mean, median, and mode all at the same value. Most normal distributions will have some kind of skew to them. So this one on the top right here is an example of positive skew because we have more values that fall on the positive side of that distribution than we do that fall on the negative side. So what that does is it brings the mean away from the peak in the data, the mode, towards the side that is skewed because we have outliers in the positive direction. And the median is usually going to fall somewhere between those two. So the median is like if we had 100 points in our data set or 100 observations, there would be 49 on the left side and 49 on the right side. Actually, that doesn't work it out exactly right. 99, 49 on each side. So yeah, based on the shape of your data set, these values can change, but for a perfect normal distribution, they're all the same. And of course, we can calculate the mean by summing up all the values and dividing by the number of observations in the data set. So outliers are interesting for mapping, right? If we don't consider the outliers, sometimes we can achieve a cleaner symbolization scheme, but they might be meaningful. So you have to keep track of your outliers. One way of identifying outliers is looking at a distribution of the data with the frequency of values on the y-axis and the actual value itself in an attribute field on the x-axis. And if you see sort of a second distribution of data with a probability peak, you might be looking at some outliers in your data. So you might, if we'd imagine plotting up the hospitalization rate from COVID right now, Montana might be out here in the outlier category. We're the only state with that higher rate. So some questions to ask yourself, right? Are these meaningful values? Are they real? Or are they artifacts of some sort of interesting aspect of your data set? So let's talk about measuring how dispersed the data set is, right? More dispersion will have more values further from the mean, median, and mode. Less dispersion, they'll all be very close to the mean, median, and mode. So here's that table of exam scores. This could also be like percent of the population with college degrees, percent of the population that identifies as non-white or non-Hispanic white, et cetera, in the demographic data. We could plot this up on a histogram, and we can calculate the variance, which is just subtracting the exam score from the mean score, and then we square it to remove negative values. So if we were calculating the variance of a 60 exam score from a 70, what you would do is you'd find that difference. In this case, it's -10, and then just square it to get rid of that negative sign. So there's no substantial difference between values that are further from the mean on the negative side versus the positive side. And the standard deviation is just the square root of the squared variance, right? So getting us back to values that make more sense with our data set. So kind of intuitively what that means is that if we had a standard deviation of 10, it would mean that the typical exam score, just selecting from all the exam scores that were in the class, is 10 percentage points from the mean score. So data sets with higher dispersion will have higher standard deviation values, and vice versa. Lower variance would be lower standard deviation values. And for a perfect normal distribution, about 68.2% of the data would be expected to fall within one standard deviation on either side. So if this is our mean, median, and mode right here in the peak of this probability plot, we have one standard deviation in the positive direction and one standard deviation in the negative direction. That'll encompass the vast majority of our data. A more dispersed data set or one that is skewed will look a little bit different. Sometimes we actually apply these variance measures to figure out probability. So if you're thinking about randomly selecting an observation from this data set, the probability that you pick one that is 3+ standard deviations away from the mean is like less than 0.1%. So it's often applied as a measure of confidence in scientific studies. Talked about this already. If you have a long tail in the positive direction, that's going to be positive skew. Nice symmetrical bell curve here. That is a non-skewed normal distribution. And then the opposite, where you have a long tail in the negative direction, going towards 0 instead of increasing numbers, that would be negative skew in your data set. Any questions so far? Going back to ArcGIS Online here, there are some ways to understand the variations in your data set using the built-in tools on Map Viewer. So on the left side, we have this charts button. And if we have our layer actually selected, we can click the Configure Charts button on the right side, and we can make some charts, right? We can choose between bar charts, line charts, histograms, right? So if you're just analyzing your data, what we might want to do is just get a look at the distribution of population values. You can change the number of bins to kind of probe that data. And to me, what it looks like is we have a lot of geographic areas here that are very small populations. Kind of makes sense. This would be an example of a positively skewed data set. If you tried to fit that normal distribution to this data, you have a long tail in the positive direction. You have some serious outliers here that have very high populations. So let's see what that one is. If you select it and then you go to your table, you can actually figure out which entry in your data set is represented by that population value. Turns out it's California, not surprising, most populous state in the nation. And so once you've built that chart, you can actually access it again. Over on the left side, you can bring up your distribution of population chart. It also provides you with some calculations of the statistics of your data set by field. So it'll tell you mean values, median values, standard deviations, right? In this case, the standard deviation is quite high, 7.3 million. Just kind of provides you with a nice accounting of all the descriptive statistics of your data set. Another way you can visualize this is that if we were working with that population data, you can go to the Styles tab. We've already selected our field, right? Population density in this case. We could select that population field as well. If you go under Style Options, it creates sort of a sideways histogram for you and allows you to dynamically drag your color bars, your color ramps based on the distribution of the data. So right now, we're really not resolving anything that's going on in the Western states except for California. So if we wanted to better design our color scheme so it actually shows variations in the data for most of the data set, we could drag that break between the darkest blue color and the lighter colors to kind of the tail of our normal distribution, right? So we're seeing that histogram turned on its side. We've got the mean labeled. We've got +1 sigma there. -1 sigma would be down here, not shown. And so all of these tools can help you better design your maps. The other thing we can do is turn on classification. So what this is, what I'm doing right here with the symbology pane is just saying, hey, I want a nice linear progression between these colors, starting with kind of a tan yellow, going to a dark blue. And it's just going to change linearly, right? Between that value of 2 and that value of 367. And I can drag these further apart to kind of change the slope of the change in the colors. But we might not want that linear progression. We might want something a little bit more complicated. That's where classification comes in. And we have quite a few different methods that we can choose for classification. So let me give you some background on classification. So classification simplifies the map. It creates maps that are typically easier to read. They can handle data sets with different shapes and sizes and variance levels. And different classification schemes should be applied in different situations based on the distribution of your data. I know this diagram is kind of washed out here, but it's showing us how we can apply color ramps to different subsets of our data for different purposes. So on the top there, we have shading where we have darker colors for standard deviations that are further in the positive direction from the mean. So let's say we were making a map of like educational attainment. We really wanted to highlight states or counties that had very high rates of college graduates, something like that. We could choose a color scheme like this to emphasize those values that are really far from the mean in a positive direction. If we wanted to emphasize areas that are kind of close to the average, we could put our darker shades of color near that median and mode for the data set within 1 standard deviation on either side. Or we could highlight outliers in both directions, or just values that are really far from the mean by having sort of a neutral color in the middle and darker shades on either side. You might have like a green in the positive direction and a red in the negative direction. So I showed you this example before. This is a choropleth map showing the affordability of housing from a few years ago. And this is an example of highlighting values that are far from the mean. So in this case, the sort of national average is that the median home price is equivalent to 3 years of the median income. And so that was set to be a transparent white color. So anything close to the mean is going to be, basically white on the map. More expensive areas are in this purple magenta shade, with the maximum values being about 10 plus years of the median income, equating to the price of a house. You can see that East Coast, major urban areas, South Florida, Rocky Mountain West and basically all of the West Coast fall into the more expensive areas. And then green showing us the less expensive areas, that swath from Texas, basically directly north, much more affordable than the average house in the nation. All right, so let's go through some different schemes for classification and talk about their advantages and their disadvantages. Here is a histogram showing us a sort of rectangular data set, right? There's not really a peak in the frequency of values towards the middle of the range of the data. We would refer to this as a rectangular distribution of the data. And this is a great application for the classification scheme called equal interval. And so for a very simple example of equal interval, you might have a range in your data from 0 to 12, and you decide you want 3 classes. In that case, you would put a class break every 4, right? It would be 0 to 4, 4 to 8, 8 to 12. That would set up 3 different colors in your data set, 3 data classes. Equal interval is really easy to calculate. It makes the maps very intuitive. We've seen a few examples of this already with like election maps. The voter turnout or the voter preference between parties was mapped with like 50 to 60%, 60 to 70%, et cetera. That's all examples of equal interval classification. So the disadvantage here is that it really only works well for these rectangular shaped data sets. It's going to be a problem if you have gaps in your data. Like imagine if there was just no data in this range right here. So let's just say we erased all the values with 8 and 9. You had a gap in your data set. You could end up with a class on your legend that actually does not appear on the map because there's no values that fall within that range. So it's very intuitive, very simple, can be very easy to read, but the classification scheme does not adapt to the data, and you have to be really aware of what the distribution of data is in your data set. I'm going to hop back over here to my map. Let's apply an equal interval classification to our population density. We can see the range in the data here. Our smallest value is 1.28. I'm just going to set that to 0 for legibility. Make our legend look nice and tidy. Going to round this off to about 12,000 just by changing those values. And it's going to automatically calculate the class breaks for an equal interval classification with 4 different classes. We have the choice in ArcGIS, both desktop and online, of just increasing the number of classes and seeing how the map looks as a result. In general, you want to use as few classes as possible just to make the map easier to read. But as you're noticing, as I increase the number of classes, you get a little bit more resolution in terms of the trends in your data set on the map. But the legend becomes more busy, it's kind of trade-offs. So you want to find that optimal number of classes that does a good job. For me, I'd say at least 6, so you can see some of the changes in the Midwest. Make sense? Right. And conveniently, we can also kind of modify the equal interval classification to have nice round numbers. This is a great strategy for map design. It makes your map much easier to read. But you have to choose an appropriate number for the range of values in your data. For some reason, my browser is like not cooperating here. choose 100 instead. So that'll round all of the class breaks to the nearest 100. So it won't be a true equal interval, but it'll be pretty close. That looks a lot better than the random numbers that were generated by the software without any modification, right? This is all part of the map design process. Okay, what about quantile? This is when you look at the distribution of your data and you set class breaks so that you have an equal number of observations or an equal number of values in each bin. So for example, with this kind of theoretical data set on the right, we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 10 observations in each class. And so the range of values encompassed by each class will change based on the distribution of your data. So everything between looks like 0 and 3 is going into one class, but this class, the next class is smaller. It's only going to show you between 4 and 5 because there's more data that falls into that range. And up here we have a frequency peak, which resulted in only the value of 18 falling into one class. So usually this is applied when there is some need for an equal number of values in each class. Like you might even be splitting up features on a map to monitor or inspect. It works well when values are evenly distributed across the range, or in other words, rectangular shaped on a histogram. But it can get a little weird if your data set is not the right shape. Outliers can cause major problems and cause classes that have a huge range in their values. So you kind of lose a lot of your spatial resolution. Let's check out an example of this. I'm going to switch my variable just to show this a little bit better. Switching my attribute field here just to total population. And let's go with the choropleth map visualization, which is referred to as counts and amounts color on ArcGIS Online. We can see our distribution of the data, right? I've already kind of set it up. It's actually automatically recognizing that the dark blue should take over right there. But let's classify the data. So we just talked about equal interval, right? Doesn't do that great of a job at symbolizing most of the states. And the reason is that we have some states that have such high populations that they're kind of drowning out all the change for the other states. Like the majority of states on this map are all falling into one class between 500,000 people and about 10 million people. And because California has such a large population, you know, it's basically defining a class of its own over here with 29 million to 39 million. Probably not the best classification choice. If we want to show more trends in the data, quantile actually does a pretty good job. Let's round these classes to the nearest 100,000. And I'm going to increase it to 5. So now we actually get a little bit better resolution on our map. We're seeing more trends in the data. We can tell Colorado is more populous than Montana, for example. But there still might be some issues, right? There's a huge range in the data for this highest population class between 21 million and 40 million. That's a much larger range than there is between 3.6 million and 7.7 million. So those class breaks are dynamically adjusting so that there are 3 states in the highest class. And actually, because so many, it's actually having trouble. How did it do that? Quantile. That looks a little bit better. So yeah, when I chose round classes, it had trouble with that, but now it's going to have an equal number of states with each color. So in this case, 50 divided by 5, there should be 10 states in each class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're picking up on a lot more trends, but in this case, the problem is even worse with that highest value class, right? The range is from 9 million to 39 million, whereas the lower classes are only between 1 and 3 million. So you're losing a lot of resolution on the high end of your data set. All good? Any questions? You might have noticed that the software defaults to natural breaks because natural breaks is a little bit more intelligent than the other ones. It actually pays attention to the distribution of data when it is setting the class breaks. And the way that natural breaks classification works is it looks for rapid changes in the values in your data set, and it tries to place class breaks where there are big changes. So we can visualize this with, like, if we sorted our data from low values to high values, starting with a value of about 5, ranging to a value of about 30. The ordinal position, right, is just like the index for that value. 1 would be the lowest value and 23 would be the highest value. If we plotted out the value based on the position, we can plot when the values are changing rapidly and when they're staying the same. So if we have a steep slope, the values are changing quite rapidly. If we have a flat slope on this type of diagram, the values are not changing very rapidly with the each subsequent row. And this is essentially an algorithm that tries to find the optimal places to put the class breaks based on when the data set is changing quite a bit. So for example, here we had sort of a lower slope that goes to a steeper slope, class break. Steeper slope changing to a shallower slope, class break goes right there. Shallow slope going to a steeper one, another class break. So it's looking for changes in your data set and it's trying to optimize the class breaks based on that approach. This is also called Jenks, named after the person who first described this technique. It's a great place to start if you don't know which classification scheme would be best, because it does respond to the actual distribution of your data. It's kind of intelligent in that way. It's trying to minimize the variance within the classes. That's another way of thinking about it, right? It's trying to find groupings that have the smallest standard deviation. Very good for ordinal data, right? If we talked about ordinal data before, like rankings from 1 to 10 that are not necessarily quantitative data. It's very good for this purpose. And it can take sort of the human bias out of the picture because it's actually just a mathematical calculation. Here's another view, right? Just trying to minimize the variance between the class breaks. And that can result in classes that have a much larger spread in the data. So let's go back to our map example and see what that looks like. We're going to choose natural breaks. We can modify the number of classes. Let's do 6 in this case. And I think this is, like, it doesn't show, maybe it doesn't look quite as pretty as the quantile classification, but it keeps the classes to a reasonable range in values, like 2 to 4 million, 4 to 7 million, 7 to 13 million, 13 to 21 million, 21 to 39 million. A little bit better than quantile there in terms of covering the population changes for the highest population states. Right, remember that quantile example, we had 10 states shown with the same color as California, whereas in this case, it's only 2, California and Texas. So really good general purpose classification scheme. If you don't have a specific reason to use a different classification scheme, you probably want to use this one, but it is always good practice to try to round the numbers off to at least the thousands. Or you might be able to get away with like 10,000 just to make your map a little bit more readable. We can also do standard deviations, right? This is great for when you have a field that you expect to have a normal distribution. Let's check out what this looks like. I'm going to choose a different attribute field. Of course, I'm missing all my actual field descriptions. Let's go over here to my tools are disappearing because I zoomed in too far. Let's add a chart. Let's try to find a attribute field that is actually roughly a normal distribution. I'm just going to guess at some of these. Give it 3 tries, and if it doesn't work, it doesn't work. Four tries. It's not working. Let's go back to the PowerPoint. So imagine you have a nice normally distributed data set. This is a great type of symbolization scheme to apply, a great type of classification. And it's going to set class breaks, starting with the mean as the first class break, right at the peak frequency of your data set, ideally. And it's going to set class breaks at either a half standard deviation or a full standard deviation on either side. Take a look at what this looks like. Let's classify using standard deviation. We can select between a half and 1 standard deviation. Let's choose a half standard deviation. That'll give us more class breaks, right? Actually double the number of class breaks. And you can't actually choose how many class breaks you have because it's going to set that based on the total range of your data set. So it's going to have as many standard deviations as is required to encompass all of the data. I don't think this classification scheme does that great of a job with that population density variable, right? It's not really showing too many trends in the data set. We can tell why, because it's not a great normal distribution. We have some serious outliers up here with much higher population densities. So this term is kind of interesting because technically unclassed is a classification scheme, but it's actually the default, right? It's when you're just stretching colors between the minimum and maximum value in your data set. The advantage of doing this would be that you could theoretically have a different shade of a color for every numerical value in your data set. So if someone was trying to recover that data very precisely, they could. But it's going to create the hardest to read maps. And if you have more values in your data set, you're going to have way more colors. Just makes it more complicated. So yeah, let's look at counties and just recap these classification schemes real quick. This is counties from the 2000 census. And if we used an equal interval classification with 5 classes, big problem, especially with counties, the really high population counties require that you have classes with really high range of values, like between 7.6 million and 9.5 million. And there's classes that don't even appear on the map, right? We don't see this orange color anywhere on the map, or maybe just right there near Chicago. But yeah, it's not doing a great job. It's not showing us trends in the data set. Quantile looks a lot better, but you can't tell the difference in this case between like Los Angeles County and these counties in the rest of Southern California, even though there is quite a substantial difference between population. It actually does a pretty good job for Montana, I'd say. Like the major urban areas in Montana pop out: Billings, Bozeman, Missoula. But for other states, doesn't do a great job. Natural break's a little bit better. It's showing us the high population counties, but still on the low end of those population values, you're not getting a lot of resolution. And then standard deviation in this case showing us higher population values and lower population values. I think out of all of these, probably the quantile works best, but it really does depend on what you're trying to communicate. All right. Have a good time in lab. See you next week.